you have any questions?
We last left off with the pole and the barn. I am going to drop backwards a second here. A couple things that I skipped over. We'll eventually actually do the pole and barn problem. All right, so I have a rocket that's basically going off to planet X and back. So it's doing a round trip. I have some identical twins. One in the rocket and one on Earth. They are exactly the same age. At the moment the rocket passes the Earth, they are exactly the same age. Rocket goes out to the other planet, comes back. Now, from Earth's point of view, the rocket's traveling at 0.9 times the speed of light. And so, if you do those calculations, if beta is 0.9, gamma is 1 over the square root of 1 minus beta squared, which is 1 over the square root of 1 minus 0.9 squared. And do you have a calculator? So if the person on the rocket is gone, ages by 1 year, so the person on Earth will age by 2.29 years. So think about similar to the muon experiment, that the muon, from the Earth's point of view, was traveling near the speed of light. The muon, not as much time passed for the muon as it did for the people on Earth. Here, we have a rocket traveling out and back. He ages by a year. People on Earth age longer. So these identical twins, still identical twins, but not the same age. All right, questions? All right, from the rocket's point of view, What the rocket sees is, I almost feel like I need a longer board. I'll stick them in the middle. All right, so from the rocket's point of view, Earth and X are traveling at 0.9 times the speed of light. The Earth goes there and it comes back. So initially going, beta is 0.9. And planet X comes here and then goes back. Initially, or with that beta equals 0.9. So in the second viewpoint, the rocket is still and the Earth is moving at the speed of light. So by this reckoning, if the people on Earth aged 1 year, oh, that's right, there's the twin there, then the person on the rocket would age 2.29 years. So if the rocket passes by Earth, it hits planet X, comes back, or in the second point of view, planet X comes to the rocket and then goes back and Earth returns, there's a difference about which one would be older. But only one of these can be correct. Because if the rocket returns to Earth and stops, one of them will be older than the other one. But the question is, which one? Is this the correct scenario, or is this the correct scenario? And the follow-up question is, which one of those, first question is, which is correct? And the second question is, what's different between them, besides point of view?
Can you explain how that one is 2.2, the rocket spot?
This one?
Yeah.
If I'm making the claim up here that the Earth is at rest and the rocket's traveling near the speed of light, that the person on the rocket will not age as much as the person on the Earth. But could I also not just look at it from the rocket's point of view? And the rocket doesn't move, it's the Earth and planet X that move, as opposed to just the rocket going back and forth. Because from the rocket's point of view, X gets closer to it, and then X goes away as the rocket returns to the Earth, or as the Earth returns to the rocket. So from the rocket's point of view, the Earth is traveling near the speed of light. So from the rocket's point of view, it seems like then the Earth is not going to age as much.
I'm guessing that one is right.
Guessing this is the correct one? Any particular reason why? Okay, gut feeling. It actually turns out this is the correct one.
Oh.
But what is the physical difference between these two situations? Not just point of view. There's more of a physical difference between what's happening in this. All right, so let's go with your planet X. Earth is over here. I'm the rocket. All right, so from your point of view, I'm coming towards you. Get here, I turn around. From your point of view. From my point of view, you get closer to me, then you stop and turn around. So, physically, did you feel that? Did I feel it?
Yeah, because you're coming.
Yeah, keep going.
And back. You're the one traveling.
Not you? what's the difference then between my traveling and your traveling? Isn't it just a matter of point of view?
Can you explain one more time? From what I'm understanding that the rocket is going.
But is there any difference? Because in physics, I should be able to look at it from a different point of view, different reference frame, and still get the same answer. So so we have the people back on Earth, the rocket's going, coming back. In this point of view, the Earth is not moving. Rocket's the one doing the traveling. In this point of view, the rocket's not moving, Earth's doing the traveling. Similar to if I walk towards you, one point of view is you're not moving and I am. The other point of view is I'm not moving and you are. But there is a physical difference between those two situations, between my moving versus your moving. So, what does it mean to feel something? Finally got some help. All right. We're working on the twin paradox right now. Recapping, we have twins. One on Earth, identical twins. One on Earth, one in a rocket, going near the speed of light. 0.9 times the speed of light. The rocket goes to this distant planet and comes back to Earth. So from the Earth's point of view, the rocket goes, comes back. If we think about the muon experiment, that the muons time did not pass as rapidly for the muons as it did for Rossi and Hall. So age, the twin in the rocket will age less than the person who stayed on Earth. So even though they're identical twins, they will not be the same age. Case number 2, we change the point of view. First point of view, Earth's point of view, Earth stays still. In the second point of view, the rocket is staying still. And from the rocket's point of view, it's the planets that move out and then come back. Now, if we look at it from that point of view, it would seem that the Earth is moving near the speed of light. And so, therefore, it seems like the people on Earth are aged by a year. The people in the rocket will have aged 2.29 years. But if the rocket goes there and comes back, or the Earth goes away and comes back, if they meet up again, one of them will be older than the other one. And what we established is that, or I guess what I have stated, this is the actually correct scenario. This does not happen. I mean, the point of view is legitimate, but there's a physical difference between these two scenarios.
And you're asking what is the difference?
Yes, besides point of view.
From the Earth's point of view, you said the rocket is moving, and
Yes.
the Earth is normal orbit, right?
Yeah,
And the
we can pretend they're staying still. The orbit of the Earth. If I'm going to a distant planet, assume not in our solar system, so the orbit of the Earth is tiny compared to how far we're traveling. So we can pretend the Earth is still.
Well, from the rocket's point of view, you say it looks like a
difference.
The speed difference?
Yeah, I'm just coming up with.
Oh. Well, from the Earth's point, in the first scenario, the Earth says the rocket's going 0.9 times the speed of light. In the second scenario, the rocket says the Earth's going 0.9 times the speed of light. They agree that something is going 0.9 times the speed of light. All right, so Erica, the next bit was, so just trying to put it more tangible. I'm gonna walk towards you and then walk away. So from your point of view, I'm getting closer to you and then to get farther away. From my point of view, you're getting closer to me and then you get farther away. And the question is, did you feel the difference between those two scenarios? Did we feel anything different in those two scenarios?
No. Oh, well, I guess just by distance, that's the only thing that's different. And,
What do you mean?
well, you got closer and then you got further back.
No, you got closer and then went further back.
You're the only one moving.
Really?
I'm sitting still.
How do you know I wasn't?
Oh. Well, I saw you were walking towards me.
So, what would I feel that you didn't feel?
I don't know.
Let's, and we can simplify it even more. I'm on a frictionless surface here. I push against the table, I slide towards you, I push against that table, slide back. From your point of view, I came towards you, I went away, I'm not walking anymore. From my point of view, you got closer to me and then you went away. What would be the difference between my experience in that and your experience in that?
Guess you experience acceleration or speed.
No, we both, look, but we're experiencing speed right now, if you think about it, because we're on the Earth is spinning, and we just don't notice it.
Yeah.
So, but acceleration is the key there. You did not accelerate,
Right.
I did.
Mhm.
And that is the difference between these two scenarios. So, at this point right here, everything changes. So up until the turnaround point, both points of view are fine. The numbers, I guess that's half the trip. He will have aged a half a year and he will have aged whatever half of that is. And up here, he'll have aged by half a year and he'll have aged half of that, 1.145 years. But at the point when the acceleration happens, there's a major shift. And because, now to get into the weeds of it would involve an accelerating reference frame, which is not special relativity, it's general relativity. However, do note that there is a difference between the two. Special relativity deals with non-accelerating reference frames. So, in this case, rocket feels acceleration. So I just at least wanted to point out the fact that there is a difference between these two scenarios. And it is, in essence, the resolution of the twin paradox. That one, oh, GPS satellites. Topics I did not go over before that I meant to hit. That's Frisch and Smith. Oh, and just a minor correction, the Echo Lake is higher up than Denver, Colorado. I think I had that reversed. There we go. All right, GPS satellite. All right, the orbital radius of GPS satellite is 2 times 10 to the 7th meters. Okay. It is in orbit, so first let's figure out how fast it needs to go. Why does it orbit? Or what are the forces acting on it?
On the E?
On the satellite.
This one.
There's a satellite here.
Gravity?
I'm gonna nitpick it.
Mm,
Gravity, huge topic.
right. I don't remember how we used to answer
Just
that.
force due to gravity.
Forced to.
All right, so we have the force due to gravity acting on it. That's, we assume there no air resistance when you're 20 million meters away from the surface of the Earth. So if I plug in F equals ma, and I'm going to choose towards the center as positive, then we have the gravitational force equals m v squared over r. This is massive satellite. And v squared over r, it's in a circular orbit, centripetal motion, centripetal acceleration. The generic formula for gravitational force, what is it? This is for either of you.